All right, so this is that time of year where we're going to start reviewing for the EOC and move forward. So the first thing you have to know are the properties of parallel lines. So remember, parallel lines cut by a transversal, your angles are either going to be congruent to each other or supplementary. So all the x's are congruent to each other, all the o's are congruent to each other, but if you have a situation where you have an x and an o, then they're called supplementary, so they add up. So in this situation, we've got our parallel lines are here, and our transversal line is here. So you're looking at this angle and this angle. What we call that, those are corresponding angles, right? So those are going to be equal to each other. So when I set up my equation, I'm just going to say x plus 9 is going to equal 2x minus 21. And then I'm just going to solve for x. That's going to be 30 equals x. And the key is to know how to set up the equation, right? So for number 2, if I extended this out and I made this my parallel lines and this my transversal line, I'd see that it's exactly like that situation there. Those are called same side interior. Same side interior is supplementary. So you're going to add 3x plus 2x, that's 5x. Negative 14 plus negative 16, that's negative 30. And that's going to equal 180. So then you're going to add 30. 8, 9, 10, 11. It's 210, so you got 5x equals 210, and I believe x would be 42 in this situation. And then the third example, here you can see that you've got this position and this position, and those are both O's, so that's alternate exterior angles. So they're going to be congruent to each other. So I'm going to add 3x, 8x equals 176, and then you just do 176 divided by 8, it's 22. So again, you have to know the relationships to know how to set up the equations to get it correct. So down here we're going to determine, so now we're going to work backwards, so we got to look at the situation to see if we can make them parallel. So we want to know if AB is parallel to CD. Well, this angle and this angle are congruent. Those are alternate exterior. So yes, based on alternate exterior angles, those are congruent. Here, there's a couple things we have to do. First, we have to figure out what x is, and then plug it in to see if they're parallel. So the first thing I can do is see that these angles here are going to be congruent to each other because they're parallel lines cut by a transversal. So I can use that to figure out what x is. So 3x plus 18 equals 4x. So x equals 18. And now I know that all three of these angles in this triangle are going to have to add up to 180. So that's 6, that's 9x equals 180. So let's see, x is 20. And since 20 does not equal 18, those are not parallel lines. The last one is going to be similar. I see that this angle is here and this angle is here, so those are vertical, so they're going to be equal to each other. 2x plus 11 equals 3x minus 9. So I'm going to add 9. What is that, 20? X equals 20. Now you can plug it in. So 3 times 20 minus 9, that's 60, 53, no, 51, excuse me. And here we've got 6 times 20, which is 120, plus 9, which is 129. And if you add those together, yep, you get 180. So that is true. So this is the only one that's not parallel. All right, using slope to determine parallel and perpendicular lines. Remember, for parallel lines, you want to have the same slope, and for perpendicular lines, opposite reciprocal slopes. And so first you have to know where slope is. So slope is always that number in front of x. Well, here we've got same slope, so these are parallel lines. And that's the symbol for parallel. Again, I'm just going to highlight the number in front of x because that's my slope. And you'll notice that they're opposite. This one's negative, this one's positive. and the numbers are opposite each other, so these are going to represent perpendicular lines. And then lastly, if you move x over and then divide by y, you end up with 2/3. And if you move x over and divide by y, you end up with 3/2. There's no relationship here, so this is neither of those two. All right, and down here, this is our congruent postulate. So we're looking at HL, SAS, AAS, SSS. What else we got? ASA, and that's it. So one of those. All right. So here, because these are parallel lines, alternate interior angles are congruent, and we have another set of parallel lines. Alternate interior angles are congruent, and then the side in the middle is congruent, so that would be ASA. Here we got side, angle, side. The angles are congruent, and then we know the two sides. And over here, this would be angle, angle, side. Those are vertical angles, these are right angles, and then the side. So angle, angle, side. So a quick review. If any of that is confusing to you, you might want to go back and study. All right, let's go ahead and learn the new stuff. So basically, we're going to talk about polygons today. So polygons are formed by 3 or more line segments. Okay, so you got to have at least a triangle to have a polygon. Each side intersects exactly 2 other sides, so the shape is closed. And then only the end points of the sides are points of intersection. So there can't be any crisscrosses or vertical angles or anything like that. Okay, so you want to circle the ones below that are polygons. Well, this first example meets all 3 requirements. This one does not, and that's because of number 3. Does not meet the requirement for number 3. This one, yes, that looks like a good polygon to me, and this one does not. And that's because it must have 3 sides. So this doesn't meet the requirements for number 1. And this one, notice how it's a blank space right here. So this doesn't meet the requirements for number 2. So that's a counterexample. So if you wanted to draw your own polygon, you could draw a nice little triangle, right? Like that. All right. Now, just remember that when you have a polygon, the point at which the sides intersect is called a vertex. So if you were to draw the vertexes on this duck sign, it would be all these corners here, any one of those you could have labeled. So then you can have a convex or a concave polygon. And the way I like to look at it is the corners, I look at them as arrows. So if you notice, this here is an arrow going out, like this, and this is an arrow going in. So if there is one arrow going in, we call it concave. If all the arrows are coming out, we call it convex, okay? And then a polygon is regular if it is both equilateral and equiangular. And so a good example of that is an equilateral triangle, where all the sides are equal and all the angles are equal as well. So if a polygon's not regular, we call it irregular. So that means not all sides or angles are congruent. So that means just one side being 1 centimeter off makes it irregular, excuse me. All right, so you're going to tell whether these polygons are regular or irregular. So first of all, if I look at this one here, all the sides are the same, but I notice the angles are not, because these are marked with 2 tick marks and these are marked with 1. So that's going to be irregular. And here too, I've got all these 90-degree angles, but what about this angle here? That's not equal, so this is irregular. And then here, I've got all 90-degree angles, and all my side lengths are congruent, so that's regular. I'm sorry, this is also irregular because the side lengths are different, right? We've got several different side lengths here. All right, now we want to say whether it's concave or convex. So again, if I can draw arrows like this and all of them are going out, you notice this corner matches this corner. That's why I draw an arrow. So then I'm going to call this convex. And here you'll notice I've got arrows pointing in, like that. So this is concave. And this one's convex, because they're all pointing out. All right. So that's a quick review of what concave, convex, regular, and irregular are. So basically, an equilateral triangle is regular. A square is regular. And we'll learn more shapes as we go forward. All right, another key vocabulary term is a diagonal. The diagonal is from A to C in a polygon. It cuts shape in half diagonally. You can also do it from B to D. So this particular quadrilateral has two diagonals. All right, the next thing we got to know is what do we call our polygons? So a triangle has 3 sides, a quadrilateral has 4, a pentagon has 5, hexagon is 6, heptagon is 7, 8, 9, 10, a dodecagon is 11, and then this we just call it however many sides it has. So if it has 12 sides, we call it a 12gon, okay? So on and so forth. Now we're going to talk about the measure of the angles, but I want you to understand that the sum of the measures of an interior of a quadrilateral is actually 360 degrees. And now I'm going to show you why that is. So remember, the sum of the interior angles in a triangle is 180, and that each, if you had a regular, this is for a regular, or an equilateral, each of the measures of those angles is 60. Or we're going to come back to this chart, so be ready to flip back and forth. Mark kind of where it is in your packet. All right, so let's do an exploration. So this is why quadrilateral, which is 4-sided, has 360 degrees. All right, so the first thing we're going to do is we're going to turn this into 2 triangles. Okay, just like that. And now, how many degrees are there in each triangle above? Well, this one has 180 degrees, and this one has 180 degrees, right? So each triangle has 180 degrees. So what's the sum? So 180 plus 180 is 360. And so is this always the truth? Well, let's try this one. If I cut this shape in half, and it doesn't matter how you cut it, I have now made 2 triangles. They're not equilateral triangles, but it doesn't matter, because this one's going to have 180 degrees, and this one's also going to have 180 degrees. So yes, it's always going to be true. No matter what quadrilateral you have, the interior angles will always add up to 360 degrees. Now let's think about this. Can we apply this? So go back to your chart. Quadrilateral, measure of interior angles, 360 degrees. Okay. Can we apply this to other shapes? So look at this pentagon. How many triangles can it make? Well, it can make 180, 180, 180. And it doesn't matter. I could also cut it this way, and I still have 180. So this one's 180 times 3. So 540 degrees. Right, so let's go back to our chart for a pentagon. It has 540. Okay, let's look at a hexagon. So a hexagon is here. It's got 6 sides, so that's 180, 180, 180, 180. And it doesn't matter how you cut it. That's why I drew another one. You can cut it like this too. So this is 180 times 4, right? 8 times 4 is 32. That's 720. Does anybody see the pattern? Hopefully you're thinking, what is the pattern here? Right? So what you should notice is that we took the number of sides minus 2 and multiplied it by 180. So